Hello and welcome back. Due to the force directly applied to the earth, we get strain. We can draw in the x-axis direction, and we have a stress which we can plot in the y direction. And since the force is gradually applied from 0 and increasing, then we'll find out that from 0 to point A we have same like line. This line is called, the slope of that line is called Young's modulus, which is the value of the stress divided by the strain, because this is tan alpha, the stress until point A divided by the strain until point A. If tensile force is applied to a steel bar, it will have some extension. If the force is small, the ratio of the stress and strain will remain proportional, and the graph will be straight line up to point A. So from 0 to A is the limit of proportionality. If the force is considerably large, the material will experience elastic deformation. But the ratio of the stress and strain will not be proportional from A to B. What will happen? That for a short value, small value of strain, it's accompanied by increase in the stress. So we get point B, and then there will be strain here, and we get what's called yield strength. So this is the elastic limit, and beyond that point the material will experience plastic deformation. The point where plastic deformation starts is the yield point, which is shown as point B. So this point, there is a considerable increase. If we are going to talk about tension, there is a considerable increase in the strain, not accomplished by increase of the stress. Almost it is horizontal portion. B is the upper yield point. Resulting graph will not be straight line anymore, and C is the lower yield point, and D is the maximum ultimate stress, and E is the breaking stress. After that there will be a fracture. Continue testing the sample will yield another point where will be increase in the strain accompanied by great amount of stress increase, and then we continue until the sample will fracture. Based on Hooke's law, we can get a relation between stress and strain. That Hooke's law is saying within the proportional limit, which is the linear part of the graph, strain is proportional to the stress. Young's modulus of elasticity, within the proportional limit, stress is proportional to strain, hence the slope, this is represented, the slope is called E, and the stress, which is the ordinate, will be equal to the modulus of elasticity multiplied by the strain, whereas E is proportionality constant, known as the modulus of elasticity or Young's modulus of elasticity. This constant of proportionality is called Young's modulus of elasticity and is denoted by the capital E. E has the same unit as the unit of stress, since the strain is dimensionless. E is sigma divided by epsilon, and the unit is Pascal. Modulus of resilience is the area under the curve, which is marked yellow area. It is the energy absorbed by the unit volume up to the elastic limit. This is the triangle denoted by M. So the modulus of resilience is the area under the curve, which is marked by the yellow area, and equal to the half of sigma multiplied by epsilon. And if we could utilize the interrelation between them, that the stress is the force divided by the area, and the strain is delta L over L, and due to the relation between stress and strain, we get that expression 0.5 FL over AE. While the modulus of toughness is the area of the whole curve from point O to E, the energy absorbed at unit volume up to the breaking point, which is this one. This is the modulus of rupture, the area of the curve starting from that point until the fracture E. This is the modulus of toughness and the area of the whole curve from point O to E. What about brittle materials? The brittle materials will reach the rupture very quickly as compared to other similar sample. If you are testing two samples, one with brittle and the other one ductile, we'll find out that for the brittle materials that the rupture is being arrived in very early amount of stresses. And so if we draw the strain and stress, we'll get that point where sigma upper is equal to the sigma at point B. Having hardness and rigidity but little tensile strength, breaking readily with a comparatively smooth fracture as glass and easily damaged and destroyed. That's why it could be assumed that it is fragile. But while for ductile materials, they are having large tensile strain up to the point of rupture. Here we start from zero, coming in the modulus of elasticity in the linear portion. Again we come to the yield and coming up. In order to reach the rupture, we have strain starting from point O2 until the end of point 25, so we have a considerable strain range. While for the aluminum alloy as compared, we have also linear portion and there is a strain varying from 0.004 till 0.2 until we reach the rupture. How we can measure the ductility? The measure of ductility could be measured by two ways. Standard measure of the ductility is the percentage of elongation. The percent of elongation is LB minus LO divided by LO, where LO is the original or initial length of specimen and LB is the length of at rupture at point B, where B here is denoted by the point of rupture. So we are getting the length of the specimen at rupture. We deduct from the original divided by the original length. There is another way of measure of the ductility, which is sometimes used as a percentage of reduction of area, because we have change in the area due to the applying of forces. Instead of length of rupture minus original length divided by the original length, we are substituting, we can say that's E naught minus sub B, denote respectively the initial cross-sectional area minus the minimum cross-sectional area at rupture. For structural steel, the percent of reduction of area is from 60 to 70% in common. Thanks a lot and see you next time.